All right, Calculus 5.2 today, we are going to learn about the natural logarithmic function and the integration. If you remember the other day, we had just done that the derivative of the natural log of u was du over u, or you can say u prime over u. Well, if we take that backwards and we integrate this on the right and it would go backwards, that's what that's telling me here. So if I integrate du over u, that would equal the natural log of u plus c. One of the reasons that works is because if I had had the integral of du over u and had rewritten it as u to the negative 1 du. So if I had rewrote it like that, if I add 1 to that exponent, that would be 0, and then divide by 0. We can't do that. See, so when you go to integrate your normal rules with this, and you add 1 to that exponent, you get a 0, divide by 0 can't. So that will remind you to go back and go, oh, that's my natural log rule. So we're integrating 2 over x dx. So this 2 right here is just the coefficient, so it would be like it's out front and have dx over x. Well, the integral of that would be natural log of x and then plus c. And we have to do absolute value because the x's here could have been a negative value, but we can't take the natural log of negative values. So therefore we have to do the absolute value. All right, on the next integral, we're going to be doing our U-substitution. See, I cannot integrate that the way that is. So if I was to let u equal the 4x minus 1, and then my derivative of that, I'm sorry, I didn't finish this. You could bring this 2 back up top. So you could leave that as your answer, but you'd have to have the absolute. If you bring it up top, that x squared's positive. You don't have to put the absolute value bars. You can, and it would not be wrong. All right, so back to this one. Sorry about that. So this u is going to be the 4x minus 1. So my derivative of that is 4 dx. I need this to be a 4 here. So if I need that a 4, I need a 1/4 out front. Therefore, we have a 4th of the integral of 1 over u du. Therefore, a 4th of the natural log of u. Plug back in for your u, and there is your rule. It says, find the area of the region bounded by the graph of f of x, the x-axis, and the line x equals 3. Well, first off, I'm thinking about that function right there. I do not have any vertical asymptotes. X squared plus 1 will never equal 0. But I do have a horizontal asymptote of y equals 0. So I have my vertical asymptote, none. Horizontal, y equals 0. It doesn't have an oblique if it has a horizontal. And this actually happens to be symmetric with the origin. If I was to put negative x in for x, the numerator is the opposite, but the bottom goes back to the original problem. So therefore, it would be the opposite of the original function, which makes it symmetric with the origin. So at this point, then, if I was to plug in a couple points, let's say I plug in x is 1, that would be 1 over 2. So when x is 1, it's 1/2. If I plug in x is negative 1, then I would get negative 1/2. All right, if I plug in 2, then I'm going to get 2 over 5. If I plug in 10, I'm going to get 10 over 101. Notice how the numerator is getting larger as x's get larger, but the bottom's getting larger faster, and that's why they're going to come up and come back down towards the 0. Okay, so the graph will look something similar to this. So I want the area bounded by the graph, the x-axis, and the line x equals 3. So that means we're going to cut it off about like right here. So that means I need to integrate from 0 to 3 for this function. So integrating from 0 to 3. When I look at that denominator, it's an x squared plus 1. See, if this was upside down, I actually would divide x into each term, and then I would integrate that. But this isn't. I have a binomial on the bottom. If I let u equal that denominator, its derivative of it would be 2x dx. So if I can make this be a 2 here, therefore multiply by 1/2 out front. Now that integrates to the natural log of absolute value of u. The u was x squared plus 1. Remember, we got to plug in 3 minus when I plug in 0. So I plug in the 3. 3 squared plus 1 would be 10. Plug in 0 would be natural log of 1. But the natural log of 1 is 0. So therefore, this is a 1/2 the natural log of 10. Or I can say the natural log of the square root of 10. All right, and then I did say to make sure you guys understand how to use this on the graphing calculator. I do want you to know how to do the integral buttons. If you don't know how to do that, please see me. You do also want to know how to do it with your calculator. Again, you will test without one, and your final exam is without one. So make sure you do know how to do it by hand, but I do want you to know how to use the calculator in case I give a calculator portion of your test. All right, so all 4 of these examples, we are integrating. Again, when I notice that the denominator has a degree 1 larger than the the denominator's degree is 1 larger than that of the numerator, typically then your denominator is your u. So if I was to let u equal x cubed plus x, well, if I took its derivative would be 3x squared plus 1. Look at that right there in that numerator. See, that's my du. There's my u. So when I integrate that, it's natural log of the absolute value of u, plug back in for your u, and that one's finished. Don't forget the plus c's. All right, in this case here, I've got secant squared on top. I got tangent on bottom. If I took the derivative of a secant, it would be secant tangent. I don't see that there for a du. But if I let u equal the tangent of x, the derivative of the tangent is secant squared x. There's my u and my du. So again, if I let u equal that denominator of tangent x, its derivative is the secant squared of x dx. Everything in the numerator is now my du, so I've got du over u for the integral. That integral will be the natural log of the absolute value of u. Plug your tangent of x in back in for that u, and there's your final answer. All right, on the next problem, I got x squared plus 2x on bottom. If I take its derivative would be 2x plus 2. 2x plus 2. Wait a minute, if I times that numerator by 2, wouldn't that be my du? See, this is where the hard part is for you guys to figure out what's your u and when do you use it. So again, the degree on the bottom is 1 bigger than that of the numerator, so I might want to try my U-substitution. If this was upside down, I would probably want to rewrite it with division instead. So I'm going to do U-substitution. My u equaled the x squared plus 2x, so the du is 2x plus 2. Well, for that to happen, this had to all be multiplied by 2, therefore by a half out front. So I have a half the integral of du over u. So that's a half of the natural log of u. Plug back in for your u, and there's my final answer. Again, the degree on the top is 0, the degree on the bottom is 1. So the degree on the bottom is 1 larger than that of the numerator. Let's try u on the bottom. U equals 3x plus 2. So my du would be 3 dx. I need to multiply that 1 by 3, therefore I need a 1/3 out front. So it would be 1/3 the integral of du over u. 1/3 the natural log of the absolute value of u plus c. Plug back in for that u, and the problem is finished. So now, what happens if my degree of my numerator is greater than or equal to the degree of the denominator? Okay, see, before on the last ones we just did, the degree of the denominator was 1 larger than those of the numerator on the rational expressions. So this time, my degree is equal. So I actually would want to rewrite this using division first. So if the degree is larger on top or equal, okay, if the degree on the numerator is greater than or equal to that of the bottom, you should do division first. So x squared divides into x squared once. Now we distribute that. So that'd be x squared plus 1. Remember, when you draw your line, you subtract. Even back in elementary school, you subtracted also. So therefore, the x squareds are gone. I have a remainder of an x, and then the 1 is gone. So with this problem right here, that x squared plus x plus 1 divided by x squared plus 1 can be rewritten as the quotient plus the remainder over the divisor. Again, that's the quotient, 1, plus the remainder, x, over the divisor, x squared plus 1. See, now when I integrate 1, I get an answer of x. Now, right here, I can do a U-substitution. See, if I let u equal that denominator, because this denominator is 1 bigger than that of the numerator, if I let u equal that denominator, my du would be 2x dx. Oh, that needs a 2. See, since this needs a 2, that means I need a half in the front of that. So therefore, this would become 1/2 the integral of du over u. So 1/2 the integral of d over u is 1/2 the natural log of u. My u was x squared plus 1. But see, don't forget that you were also integrating this 1, so that was just a plain x there. The u part only went for this second part of the integral. It did not go for this first part. And then again, don't forget the plus c's at the end, please. So again, if the degree in the numerator is greater than or equal to the degree of the denominator, then you need to rewrite these with division. You want to write your quotient plus your remainder over divisor, integrate this like normal. This piece here, I'm doing a U-substitution. So if I have 2x on the top and x plus 1's quantity squared on the denominator, and I'm integrating. So I'm going to start with the degree on the bottom is actually x squared. The degree in the numerator is the 2x. I'm going, okay. But see, if I was to FOIL out the bottom, I would have x squared plus 2x plus 1. And then if I was to try to find a du, I have an x and a constant term, and we don't have that in this problem. So this one would be a little tougher that way. So let's start with maybe just trying the u equals x plus 1. So if I do that, my du would just be plain old dx. Well, at this point, if I do my substitution, this is still 2x. There's my u squared, and there's a du. The problem is I have a mix of variables here. At this level of calculus, in Calculus 2, we can integrate with different variables in there, but not in Calculus 1. So we need to substitute for this x. So this x right here would equal u minus 1. We're going to plug a u minus 1 in here for that x. So when I do that, that's 2u divided by u squared, and then we have negative 2 over u squared. Okay, so I'm showing the steps. 2u minus 2. Each one of those is over u squared. Now, this one becomes 2 over u. And again, on my du over u would be a natural log of u, absolute value of that u, sorry. I have a coefficient of 2. But on this one, notice I did a rewrite. I brought the u to the negative 2 up to the top. Now I want to add 1 to that new exponent, divide by the new exponent. That's why that became a positive 2 right there. Again, that was the coefficient of 2 out front. The natural log of u, because that's du over u, the integral of it. Then I had a negative here, but when I add 1 to that, that became negative 1, divide by it. That right there became a positive 2u to the negative 1 plus c. Now we're ready to plug back in for all our u's and bring the exponent down for the u to the negative 1, how to bring that x plus 1 to the denominator. So the log rules for integration, the guidelines. So learn the basic list of integration formulas. Okay, so you need to make sure you know the basic ones, power rule, log rule, and so forth. You want to find integration formulas that resemble all or part of an integrand. Trial and errors. What's your u? If it doesn't work, try a different thing for u. If you can't find a u-substitution that works, try alternating the integrand. You might try a trig identity, a multiplication division by the same quantity, something. You got to be creative with these. If you have access to a computer or software, make sure you guys are able to find the antiderivatives, but you need to be able to do these by hand because your final exam and your test will be with no calculator or software. So this one tells me to solve the differential equation. Basically, solving a differential equation means they want me to find what does y equal. All right, so that means we need to integrate. So if I'm going to integrate this, I need y will equal the integral then of 1 over x natural log of x dx. I have a couple choices for my u. My u could equal 1 over x, or my u could equal just the natural log of x, or just 1 over the natural log of x. So you got to just think about all the different possibilities for it. Where would I have my du here? See, if I let u equal x, that doesn't change anything, because every single one of those x's just become u's. But if I let u equal the natural log of x, then my du would be dx over x. I have that here. See, here's the dx over x. That would be my du then. So again, there was the choices for your x, for your u's. My u could be plain x, it could be x natural log of x, or u natural log of x. And again, this derivative would be dx over x. Dx over x. See, that's why I want that one to be my u. So I'm integrating du over u, which is the natural log of the absolute value of u. Plug back in for your u. Our u was the natural log of x. So we have the natural log of x plus c. And that's my differential equation. The integral of the tangent of x dx. Tangent of x is absolutely, if you rewrite that, if I think back to my trig rules, the derivative of the sine is cosine, the derivative of the secant is secant tangent, derivative of tangent secant squared. See, I didn't have any of them that the derivative gave me a plain tangent. So I'm going, okay, well, if I think back to my trig identities, what if I rewrote the tangent as sine over cosine? All right, now let's take a look at if I let the denominator equal the u. So if u equals the cosine of x, then my du would be negative sine of x dx. So again, I'm letting u equal the denominator, then my derivative of that would be negative sine of x dx. So the numerator, except I need a negative sign here, is going to be the du. So I have negative integral of du over u. Well, then that means I've got negative natural log of the absolute value of u. Plug back in for your u. And there's the final answer. All right, the integral of the secant x. This one is tough to do. So the integral of the secant x, we just don't see this. This is where we're saying about getting creative, multiplying by a big old fancy 1. See, I know when I take the derivative of the secant, it's secant tangent, but I don't have any secant tangents anywhere here to deal with that. The derivative of tangent isn't secant, it's actually secant squared, so that doesn't help me any. So what we're looking for is, well, if I multiply this by a big old fancy 1. So my fancy 1 meaning secant plus tangent. So now I go ahead and distribute the secant of x with the numerator. So that's secant squared, and then this is secant tangent. Guys, take a look at this denominator now. If I took a look at the derivative of the denominator, the derivative of the tangent is secant squared, hint, hint. The derivative of the secant is secant tangent, hint, hint again. Oh, that means if I let u equal that denominator, then my du happens to be that entire numerator. So I have the integral of du over u, which is going to be the natural log of the absolute value of u, plug back in for that u, and then we have just proved what the integral for the secant of x is. Now, for extra credit for this chapter, if you'd like to, you can come in and you can prove the integral for the tangent of x, cotangent of x, integral for secant and cosecant of x. And so that'll get you some bonus points for this chapter's test if you'd like to come in and do those early. So again, like I said, extra credit proof for the last 4 integrals on this list. So proving the integrals for the tangent, secant, cotangent, and cosecant. That way you know what those answers should be as you work them at home before you come and actually try to do that for bonus points. All right, so we're integrating the square root of 1 plus tangent squared. And I'm looking at that and going, wait a minute, 1 plus tangent squared, I'm hoping that kind of rings a bell, Pythagorean identity, and that would be a secant squared. And the derivative of the secant squared is secant. So we're really integrating from 0 to pi fourth of the secant of x dx. Now on the last slide, we just proved what the integral of the secant of x was. So using that from our last slide, we know the integral of the secant is the natural log of the secant plus tangent. Again, you're going to plug in the pi fourths minus when you plug in the 0. Pi fourths is equivalent to 45 degrees. The secant's the reciprocal of the cosine. So cosine would have been radical 2 over 2, so you're going to flip that over. The tangent at pi fourth is 1. All right, the secant is the reciprocal of cosine at 0 radians. So at 0 radians on the unit circle, that would be over to the right. That point is 1, 0. The cosine's 1, so the reciprocal is 1. Now the tangent at 0 happens to be 0 over 1, which is 0. So that tangent of 0 is also 0. Now, once we've done that, this right here, this becomes the natural log of 1. Well, the natural log of 1 is 0 as well. So there's my final answer. All right, the average value of a function on the interval from 0 to pi fourths. So first off, 0 to pi fourths, this is a smooth and continuous curve. It is differentiable from 0 to pi fourths and integratable. So from 0 to pi fourths, and here is my b minus a, pi fourths minus 0. That's for the fraction out front, and we integrate. We had just proven what that was. So the integral of the tangent becomes, or you can rewrite it again, tangent is sine over cosine. It's kind of like going through the proof again. U is your cosine of x, so therefore my du is the opposite of what's in the numerator. So I needed a negative 4 pi, the natural log of u, which was the cosine. All right, we plug in the pi fourths minus when we plug in 0. Remember, pi fourths is at 45 degrees in quadrant 1. The cosine at 0 is on the unit circle. It'd be over to the right. The x-coordinate over there is 1, and the y-coordinate is 0. The cosine would be the x over r, which would be 1. So that equals 1, but the natural log of 1 is 0. Pi fourth, radical 2 over 2, and then we want the natural log of that. And it says this very difficult one, number 13 on the homework. All right, so I'm looking at that and going, oh boy, I got 1 over 3 plus radical 2x. So if I try letting u equal the denominator, 3 plus the radical 2x, my derivative would be 1 over 2 radical x dx. So this is what I have so far. I've got the 1 over u. Here's the dx. So I might go ahead and solve that for dx. Well, dx would then equal the square root of 2x times du. The square root of dx times du. Well, the square root of 2x happens to equal u minus 3. So I could plug u minus 3 in for that square root of 2x. So I'm going to plug all of this junk right here in for the dx. Now we can distribute our 1 over u with each of these. So therefore I'm going to have the integral of 1 minus 3 over u. That's going to be just plain old u. That's going to be minus 3, the natural log of u. And now plug back in for these u's, and you are finished with this problem. So this is another very difficult one in the homework for number 14. So again, let's start with the denominator for our u. And there's my du. So a minute ago, we went ahead and we substituted this for our u down here. Okay. The dx, we took the solve for dx. That would be 2 radical x times du. All right, now that we've done that, up here in the original problem, the square root of x equals u plus 7. So that's a u plus 7, that's a u plus 7. Going to take care of some FOILing and distributing. All right, so this would have been a 2. There's a u plus 7 quantity squared. There's my u. Once you've FOILed this out and then distribute your 2. All right, 2u squared over u will become 2u. 28u over u is just 28. But notice 98 over u, I don't write it 98u to the negative 1. Because if I do that, I'm going to add 1 to the exponent, get 0, and I can't divide by 0. So therefore, I'm going to have to leave that one 98 over u so that this one will become natural log of u du. All right, now we have to take and go plug back in for every single one of these u's. And there's the final answer. So again, you go ahead and start with that messy denominator for your u. Get your du. All right, you're going to solve for the dx to sub it in for this dx. I solved for the square root of x there because I had one of those in the numerator still, and I have one right here. So I substituted for it. FOILed and distributed everything in the numerator, simplified this expression. Remember, if it's over a monomial, you want to simplify it, and then you differentiate each term separately. That's showing you just if you were to FOIL this out, distribute, and combine like terms. But you can leave it at the first one. All right, so what would be the first step? In this situation, this would be 11 times the dx over x. See, that'd be 11 d over u. All right, my first step. That would be let u equal the x plus 9. See, the du would be dx. So this would be 7 times the natural log of the x plus 9. And of course, these are absolute value and plus c's. Just kind of doing a little quick little mini summary. All right, if I let u equal the bottom, then my du would be 9 dx. So again, I have the coefficient of 7 out front, but I need a 9. So therefore, this would be 7/9 natural log of u du. I'm sorry, that would be 7/9 natural log of u and then plus c. All right, in this situation, if I took the derivative of the bottom, that would give me 10x to the 9th plus 3. So if I let the bottom be u, everything in the numerator is my du. So therefore, it's the integral of du over u. Again, it'd be a natural log of u plus c. All right, now we change them up a little bit. See, notice here, the degree was 1 bigger on bottom, 1 bigger on bottom, 1 bigger on bottom, 1 bigger on bottom. Now the degree is 2 bigger on top. See, if the degrees are equal or bigger on top, then you want to actually rewrite it with division. I want to take x cubed, divide by x, and then 30 over x. X cubed over x would give me x squared. 30 over x would be, when I integrate it, would be negative 30 natural log of x, and then plus c. All right, in this situation, your first step would be to do synthetic division, actually. You'd want to rewrite this as a quotient plus the remainder over the divisor. All right, your first step this time would be to do long division because I have x squared and x to the 4th. Again, the degree is bigger on top. So you would want to do long division first here, rewrite it as the quotient plus the remainder over the divisor. All right, if you look at that, u equals the natural log of x because that's the messy stuff to a 9th power. So if I let u equal the natural log of x, its derivative would be dx over x. So this becomes u to the 9th. dx over x happens to be your du, and therefore then you're just integrating u to the 9th du. All right, this big old mess. I'm going, well, maybe what's in the parentheses might be my u. So if I let that equal the u, then my du would be 1/11th times x to the subtract 1 from that would be negative 10/11ths. Look at that. I've got an x to the negative 10/11ths. Now, I don't have the coefficient of 1/11th there. I'd have to take care of that. But my main idea here is what is your first step? Like, what is your u? Y'all need to be able to pick those out pretty quickly. All right, so if I have integral of 4x over x minus 2 quantity squared, I definitely have a bigger degree on the bottom. So if I start with letting u equal the x minus 2, then my du would be dx. So u squared down here. The problem is then up in the numerator, if I let u equal x minus 2, I'd have to solve for x, sub it into there for this x right there for that 4x also. That one might be a little bit tricky. Definitely has a lot more steps than the other ones did. And these were those complicated ones in our homework. We let u equal the entire denominator. We get its du. And then remember, we did solve for dx. We did solve for the square root also, and we did a lot of substituting. So this was kind of a difficult one. It's not a bad idea to take all these problems that I have on the slide and make flashcards out of these and the work and how to do them on the back. All right, so if you're integrating the secant of 7x, well, my u is going to have to be the 7x. So my du would be 7 dx. So I need this to be a 7, so I'd have to have a 7th of the integral of secant of u du. And then that's one of those new rules that we learned today. I can integrate sine of a plane variable, but not sine of 4 theta. So this time my u would have to equal the 4 theta. Its derivative would be 4 d theta, so I need a 4 here. So I'd have to have 1/4 the integral of the sine of u and then minus 9. If I let u equal that denominator, the derivative of that denominator happens to be a negative cosecant cotangent, which is what's in that numerator, just missing the negative sign. So then this would be negative the integral of du over u. And again, I can integrate cotangent of a plane variable, not a 1/11th of theta. So let the u equal the 1/11th of theta. So my du would be 1/11th of d theta. So I need a 1/11th here. That means I need 11 out front. So it'd be 11 times the integral of the cotangent of theta. D theta. I'm sorry, du then. And then just use your new rules from today. So again, like I said, I'm suggesting you make these into flashcards. All right, so there's your 4 new rules today. I should say integral of your trig rules, 4 new ones. And then here's your integral of the du over u, which was also new to you as well today. So do remember, please, if the degree of the denominator is 1 larger than that of the top, you want to let u equal that denominator. The du will work out nice and pretty in the top, typically. Okay. Now, if the degree on the top is equal or bigger than that of the bottom, then you would want to do long division and rewrite the problem as a quotient plus the remainder over divisor. Good luck to you on 5-2. We'll see you tomorrow.